Hi, hello. Thank you for attending to this new webinar. This webinar will be about composite modeling and analysis using CivilFEM 2023. Our hosts for today are Roman Martin and Ronald Siad from Ingecyber. The summary of models that we will show about these capabilities are the sandwich panel, a water tank, concrete beam strengthening, concrete slab nonlinear analysis, and a Bascule bridge.
So we are going to see CivilFEM capabilities through these 5 examples. Well, before starting, we are going to explain CivilFEM products. There are 2 different main CivilFEM products, CivilFEM for ANSYS and CivilFEM for Marc. CivilFEM for ANSYS, it's are 2 add-ons, one for CivilFEM mechanical APDL, the classic environment, and also CivilFEM works on WORKBENCH. The CivilFEM part, the CivilFEM capabilities in the mechanical APDL, well, this is an add-on, so it is fully integrated in the ANSYS graphic interface, and more than 400, adding more than 400 capabilities, and those capabilities are mainly material and cross-section library for easy definition of the models, load combinations, concrete and steel design by structure design by international codes and standards, and also a lot of capabilities for modeling and design pre-stressed concrete models, and also a geotechnical bridge and nuclear power plant models. Here are some examples of this modeling. The capabilities that CivilFEM adds to the WORKBENCH environments, these are some apps that are fully integrated in the graphic user interface of WORKBENCH, so it's very easy to work. And main capabilities are material cross-section library, load combinations by codes and standards, and concrete and steel structure design by international codes. And well, CivilFEM powered by Marc, this is the product that we are going to see today, the most powerful solution that we have. And it is the combination of CivilFEM that added a graphic interface and many capabilities, and focusing the civil, structural, and geotechnical sector. And CivilFEM is using, in this case, Marc from MSC Software Hexagon, which is a very advanced nonlinear solver. These capabilities are some of these capabilities are geotechnical capabilities, nonlinear analysis, but of course ULS and SLS design according to steel and concrete codes, and very advanced nonlinear simulations. Like in example, here we can see backlight analysis, advanced backlight analysis, concrete cracking and nonlinear materials, also transient nonlinear analysis, like this seismic load seismic analysis on a masonry bridge, with failure and cracking analysis, construction process with material time dependent properties, and also seepage structural couple analysis, where poor water pressure is considered for slope stability analysis and many other geotechnical analysis, and seepage thermal couple analysis where materials are thermal dependent, and we can analyze some cases like the collapse of a steel structure or concrete structure due to a fire in the bottom part of the model. Well, this is a basic introduction, and we are going to go directly to composite material and laminates models.
Okay, the first example is a sandwich panel. It's composed of 2 metal face sheets and foam core. Due to that, it adds lightweight. Both sheets, they carry the bending loads, and the core will carry the shear loads. The thermal and sound isolation is one of the main capabilities, and it will be the target is architectural use as walls and roofs. Okay, here the reference we are based off, it's this paper, Finite element analysis of loading area effect on sandwich panel behavior beyond the yield limit. Okay, here is the paper, and we used it as a reference. Okay,
So, well, this model, the model we are using, is a nonlinear composite material model, which is generated with a cell element and with the three different layers. And there are two metal sheets that carry the bending moment. So the distances between those metal sheets due to the foam core increase the bending resistance. But the main problem of these models are the shear capacity that can support this foam. That is a very weak material. So in this model, we have analyzed this nonlinear behavior and what happens with loads that generates yielding. So we have performed a nonlinear analysis. In this case, we have modeled different material models, material properties, and this has 8 layers. The two top and bottom layers are the ones with for the sheet materials, and the rest of the layers are the intermediate layers for the foam. So in these layers, we can see in this plot we are having equivalent plastic strain, and as the results, we can plot displacement versus loads, and we can analyze the ductility of this model. The way to define these materials are here in models. We generate some generic material models, and then for this, after generating the different material models, we generate a composite material, which is this. And in this composite material, we define the different layers and the thickness. So just with some single clicks, we define all these layers on the model with these materials. So for the core, we are using this material ARIX, which is this one. And here we have added an analysis diagram with a nonlinear plastic behavior. This is the plastic branch that it has a small yielding branch and suddenly failure. So we have analyzed these values. So as the results of the nonlinear analysis, we can see how there is no yielding at the beginning, and as we can see, yielding starts core until failure of the model. So this is very useful, this nonlinear analysis with nonlinear materials in this composite material, in the sandwich panel, to see where is the failure and maybe increasing for shear resistance. And we go with the next example.
Yes, the next example is we'll see a water tank. Okay, here it's angle apply laminated material, glass epoxy, and the target is to optimize the fiber orientation in order to get a minimum stress and strain. So the parameter will be the apply angle, and we finally obtain as well the failure criteria. And in this case, we used this paper. Okay, about composite pressure vessels. There's an introduction, and you see the fibers and the material. The process and the geometry and the different layers.
And so we can see here in this plot that we have the ply angle orientation, the fibers orientation, and this angle is what we are going to orientate. We are going to add different angles and adding different plies with a positive and negative angle. So we are going to analyze this model with starting with 35 angle and increasing to 45, 45, 55, 65, and 75. So the target of this is analyzing which is the optimum angle. So here we can see the model. In this model, what we have done is here in the tank properties, we have added 5-layer model. These layers are defined in composite material, and we can see there is an angle orientation. This angle is set by a parameter. This is the parameter that CivilFEM can use, scripts, macros, and parameters. So what we have added is a parameter, which is the apply angle, and we have set that parameter in this information. So if we modify here this parameter, 55, anything, the parameter is automatically set into the model. So what we have done is modifying this parameter and solving. And so we have extracted deformation. In this case is the deformation, which is in this case for the 45 angle. The maximum deformation is 7 millimeters in those zones. And also we have analyzing stresses. This result in example is stresses from misses equivalent stress. Here we can see the stresses. These stresses can be analyzed and set in the different layers. So we can see the different layer stresses and analyze which is the most optimum solution considering this angle. So for that we have extracted those solutions, and if we see the PowerPoint, here the PowerPoint for the different angles, we have extracted the maximum stress for misses stress, and for 35, 45, 55, and different angles. So we can see that based on stresses, the maximum stresses are, the minimum stresses are obtaining for 55 angle. If we plot the deformation, we can see that the optimum value for deformation is 45 angle. We have divided, we have split the maximum deformation into deformations in the cylinder and in the sphere lateral zones. So we can see that 45 angle is the optimum for these cases for the deformation. So going again to the model, we can see that this is the optimal solution. So in this optimal solution, we have also analyzed the failure criteria. So if we plot here failure index, we can see there are some high values over the limit over 1 in this internal layer and in the transition between the cylindric and the sphere zones. So in the inner part of that. So it will need reinforcing because this failure index is higher than 1. If we plot between 0 and 1, that is zones that are okay, we can see that well most of the model is okay, but yes, there are some zones here that goes over the limit in these parts. So well, this model for the final design would need reinforcing that internal zone, which is greater than 1, and these other areas. So with this single model, we have analyzed the optimum angle and also which zones should be reinforced based on the failure criteria. For the failure criteria, we have several methods, the maximum stress method, Hill and Hoffman methods, and also progressive failure. Well, with this failure criteria, we obtain a failure index that should be less than 1, and the progressive failure is a nonlinear analysis where every layer has a progressive failure with a default stiffness, and then with that default stiffness, the model stops converging when the model is completely, that section is completely cracked. So if we see the model, the way to define that is in here in the glass epoxy material. Here we can see that we have cracking properties that we can activate. It has a brittle failure, and there's crack like for concrete, in example, and a stress failure. In this case, that is for composite materials. We select here the different methods, maximum stress, Hoffman, or say Hill, and set the maximum allowable stress in the different directions for tensile and compression normal stress, and also for shear stress. In case this is the failure index that we set, one could be less than one, and in case we would like a nonlinear analysis, that the analysis stops when the section breaks, we should set here the progressive failure and a residual stiffness factor for every layer that goes over the stress limit. Well, okay, if we go to the next example.
Here we go. After this, the next one is the concrete beam strengthening. Okay, concrete, the original concrete beam is created with solid elements, and for the steel reverse truss elements. The beam capacity will be analyzed using three configurations: original configuration, just concrete, and it will be add a reinforcement of bending, only bending, and then bending plus shear.
Those reinforcing are added with composite material, just glass reinforcing layer on bottom and on top. So if we see the papers again,
yes, here this is the paper.
This model is based in this experimental study and for reinforced concrete. In this paper, they analyzed a concrete beam with reinforcing layer composite material bottom, and they performed different tests for seeing the incremental of the capacity and the failure. In this paper, what they analyze is only reinforcing layer on the bottom for bending, and as a resume they have is that the original situation has a failure, crack, a failure due to flexural, and for the reinforcing models, the failure is due to the shear. So in our model, we have gone further, and what we have done is adding also shear reinforcing. So if we go to those models, we can see that the original situation is this with the concrete beam. So in this concrete beam, we have solid elements for the concrete, and inside it we have rebars that are given, here is the thickness, that are modeled with truss elements. In this model, we analyzed the force versus displacement, and we obtained this curve: vertical displacement versus force. We have here the first crack, and there's a different slope in this part, and then here we start having jailing on the steel until the collapse. We can see if we plot here crack width. This is the final failure that is due to bending, cracking, and if we plot different values of the different intermediate results, we can see that how these cracks are being increased. Also we can see that there's a high crack width for the shear cracks, but the failure is due to steel jailing. We can see that here we have yielding on the reverse, the bending reverse, and the failure of this model. So well, in the next model, what we have done is adding this reinforcing, and the reinforcing is this cell element that is added on the bottom for the bending reinforcing. So well, the result we have seen is that now failure is due to shear. Now we have these shear cracks. Now bending cracks are reduced a lot comparing with this other model. Here we can see that the first model cracks, bending cracks are the most important, and the failure is due to bending. In the next model, we can see that when adding bending reinforcing with this cell layer on the bottom, this orientated composite material, now the failure is due to shear. So what we have done in the last model is adding all these shear reinforcing, which is adding these strips to the model, and so we are giving some extra capability to the model. And then if we plot crack results, we can see just in the concrete part, we can see now that the main cracks are happening on the bending part. Also, we have some high bending cracks here, but the failure is due to bending. And also, we can see the effects of the different reinforcing composite material in these zones that are avoiding cracks in those zones. But in between, we have these cracks and this failure. And well, also we can analyze the load versus displacement capacity curve, and we can see ductility in these curves. So here first we can see first crack. So here we have different slope. Here we start having yielding, and this is the plastic branch. And well, we can compare the results with the other branch with the different models. So well, going again to the PowerPoint, we can see here in PowerPoint 3 different videos with the different 3 configurations where different cracks are happening. Here bending cracking is the main failure. These are the second one is the failure is due to the shear crack and the shear yielding on reinforcement, and the last one is due again to bending or bending plus shear at the same time. So here we can see the original situation, which is this curve. When adding bending reinforcing, we have this other curve. So we are increasing capability of the section, but ductility is reduced a lot. Why? Because now we have shear failure. So well, in order to gain not only capability but also ductility, which is very important for concrete, we have added some shear reinforcing, and here we have the resume of the loads. We gain 80% of the capability when adding bending reinforcing, but when adding bending plus shear reinforcing, we add up to 20% of the capability, and ductility is reduced from 2.27, which is the ratio between the plastic and the elastic deformation. For the original situation, it is 2.2. When adding bending reinforcing, we gain a little bit of 80% of capacity of the beam, but ductility is reduced to 1.4, about 1.4. And when adding both, when now failure is due to bending, again ductility is increased to almost 1.9. So this is a very representative example of how this reinforcing works. This reinforcing can be applied to any structure or also pipelines.
Okay, the next model is a one-way concrete slab. The laminate is simulated as an equivalent thickness and orientated ply, only for the longitudinal reinforcement. Okay, a nonlinear material model is used for both concrete and steel to obtain the realistic flexural behavior for both ultimate and serviceability limit states.
So well, this is a very useful tip for modeling nonlinear, for modeling a realistic behavior of concrete for cell elements, for modeling slabs and walls. So what we are doing in this example is defining several plies for concrete, and for the reinforcing, what we add is a new layer, new ply, and that layer will have an equivalent thickness for having the equivalent area of steel, and we orientate this ply in the longitudinal reinforcing direction. So when this tip, we can model with very easy and fast models, we can obtain a very accurate deflection with this nonlinear analysis. This is a single tip. We are not going to see the model because we don't have much time, but just for you to see that here you have this is one way slab, and here you can see this is the layer of reinforcing and also nonlinear materials for modeling concrete in a very accurate and fast way.
The next example is a Bascule bridge. Okay, this bridge will rotate about an axis, and to balance the moment of the bridge deck, a counterweight is applied. Here, the light deck is important. So steel beams and a composite slab is modeled, and we will obtain the result of a progressive failure.
So, well, as Ronald said, this bridge swings all along the horizontal axis, swing vertically. So, well, just for this movement, here there is a weight, just to contrast the deck weight. So both weights are over the axis, so they could be a very high weight. Just for reducing that weight and also the engine capacity that is needed for this movement, a light deck is very important. So with a light deck, we reduce weight also in this other part for generate the movement, and also in the axis, and also the engine to move, and all about the engine is very reduced. So this is very important for that. So if we see the paper, this is basis in this paper that analyze this type of models. In this paper, there are several examples, real examples, and they analyze this deck, which is a mix of steel beams and a compression slab on top with this analysis. So this example is based on this paper. If we see the models, here now we have solved two different models. In this first model, we have generated different load combinations. The first one is the self-weight with a 1.35 factor, load factor, and different combinations. This other is the self-weight plus permanent loads by 1.35 factor, and the others are a combination of permanent plus different overloads. So here we have the permanent loads by 1.35 and also some other loads which are pressure or punctual loads on that due to the traffic, different traffic. And so, well, for this configuration, we can check the steel part and also for the composite material, the way to analyze it is through the failure index. So for plotting the failure index, here we have the different results that have been solved. The first result is the self-weight. So we can see that here in the self-weight, this failure index is very, very low. It's below 0.5%. So for permanent loads, well, that is a reasonable result because it's very light, this material. So for permanent loads also, this failure index is very low. But when we start adding different load configurations, this failure index is increased. 0.31 means we are consuming only 30% of the capability, so it's okay. Also for different loads, this is increased to 0.4. So different load configurations, different traffic loads. So we can see here these results we are having are just about less than 50% of the capability, around 0.5. So this is just for analyzing different load configurations and checking the model. We can check if the model is okay or not okay, and that the safety factor using the failure index a part of checking the steel part. But we have performed another model with progressive failure. In this progressive failure, we have increased the load up to 5 times that load. So we have added a 5 coefficient and we have solved the model. So the model is being solved until the failure happens. So failure happens when the coefficient for that load is 3.5. So we know that the safety factor for this overload is 3.4. So in this way, with the progressive failure and this nonlinear analysis, we can obtain the different safety factors of the different overloads. If we see the video in the PowerPoint of these load applications, here we can see the progressive failure when that progressive failure is happening, and we can obtain with this progressive failure the section capacity curve, load versus displacement, and also the load factor for that generates the collapse. Well, as a summary, we have seen the laminate and composite models for 5 different examples of the application of this material model. All these examples are based on multilayer cell elements, are modeled with multi-cell layer models, and the capabilities that they have is that we can use nonlinear materials on every layer with different failure on every layer, based on not only the nonlinear properties of every single material model, like we saw with the concrete and steel. Also, we can obtain a failure criteria through a progressive failure or through a failure criteria index. So this has been a very fast, we have been going very fast through these examples, so we couldn't show them in detail. But if you are interested in having further information, do not hesitate to contact us for giving you some more extra information, or also you could download a trial version, and also we could provide you these examples for you to work with.
Yes. And don't hesitate to visit our social media and stay tuned. And here you have our contact data. So thank you and see you in next webinar. Bye-bye.
Bye. Thank you for your attention.